Hello, my name is Jimmy Otzel, and I'd like to welcome you to this course on how to use the S8 downscaling tool to assist with climate change adaptation planning. This tool is a web application with a graphical user interface that allows people with the limited knowledge of developing climate models to perform dynamical downscaling and develop their climate projection models using simple click and drag functions. It was developed by the Ministry of Environment within the Government of Japan in collaboration with Tsukuba University in Japan and the Regional Resource Center for Asia and the Pacific, Asian Institute of Technology in Thailand. This learning session is intended for project managers and decision makers who seek to manage the development of climate scenarios for their regions, particularly those officials involved in the National Adaptation Plan process from developing countries, but also widely applicable to all climate adaptation practitioners. The main objectives of this session are to explain and understand the potential use of climate change and scenario planning in a strategic decision-making context, climate change downscaling, as well as its methods and applications, the benefits of using this new climate downscaling tool, the S8 Downscaler, the use of the S8 downscaling method to support national climate adaptation planning, and finally, fostering communication and knowledge exchange among users on climate information. There are 3 modules in this session. The first module deals with the basic understanding of climate information, climate scenarios, and climate downscaling. The second module deals with the understanding and operation of the S8 downscaling tool, and the third module will explain the National Adaptation Planning Process, or the NAP, and how the output from the S8 downscaler can be helpful in developing the NAP of the affected countries. The science of climate change, together with public awareness, have been progressing in recent years, while the need to address climate change has also increased significantly across the globe. In this atmosphere of continuing climate events and climate-related disasters, governments, local communities, and the civil society in general increasingly understand the potential impacts of climate change and the need to take action. Climate change cuts across many different sectors and affects people in many ways, especially in developing countries and among the poorest segments of society. Among other prerequisites, clear climate data is necessary to identify climate risks and to inform decision-making for effective risk management. In short, the quality of decision-making depends on the quality of information. Let us understand climate information as our past, current, and future climate conditions. These help us define the different climate scenarios we may face, which in turn allow us to prioritize our adaptation actions. The sources of climate information include downscale climate projections, climate information databases, weather stations, early warning systems, seasonal forecasts, climate communication reports, climate adaptation plans, and a repository of other climate-related reports. Climate information is used to understand current and future climate scenarios, assess risks and vulnerabilities, and identify adaptation options. Through the effective use of climate information, decision makers can make investment and planning decisions that are practical, robust, and sustainable. These forward-looking strategies will help to ensure longer-term sustainability and avoid decisions that will limit future options. At the same time, they will help avoid maladaptive solutions that involve making decisions in one sector that might damage other systems, sectors, or social groups, or increase the vulnerability of people and communities. What types of climate information are required? The answer depends on the purpose for which the climate information will be used, as well as the scope of the planning, which could range from risk screening and assessment to decision-making. For example, in agriculture, climate information can be used for monthly and annual precipitation records, to understand the impact of flooding on crop yields or to substantiate claims for crop losses due to inclement weather. In the health sector, precipitation data can be used to investigate the relationship between increased flooding and waterborne disease outbreaks. And business entities might use disaster and extreme event information to perform risk analyses. In general, the purpose of climate information becomes a question of what impacts we care about and what the connection is between what we are concerned about and one or more climate or weather events. Given the importance of climate information in the adaptation effort, it is no surprise that there is a growing number of national, regional, and global initiatives to improve the quality and accessibility of climate information. These efforts have produced climate reports, observed data, and climate model outputs. Such information can be accessed from national adaptation plans, national communication reports, meteorological and hydrological reports, and other sources. A great deal of notable global climate information can be accessed from the following links. Finally, beyond climate change, there are many non-climate factors such as access to markets, social networks, culture, and other variables which may play an important role in determining the vulnerability of communities. Therefore, climate information should be applied in conjunction with other relevant non-climate data with an integrated framework. Scenarios are possible future events that may develop or future situations that will help us mitigate risks moving forward. They allow analysts and decision makers to create sensible plans for adaptation. Since our future is uncertain and is subject to choices that have not yet been made, scenario analysis offers a means of exploring a variety of long-range alternatives. It enables consideration of how critical uncertainties may affect the future, thereby broadening perspectives, challenging assumptions, and highlighting hidden dangers and opportunities. Likewise, climate scenarios are storylines about how the world will develop along the possible global development pathways when considering the amount of greenhouse gas emissions in the future. According to the Intergovernmental Panel on Climate Change, or the IPCC, a climate scenario refers to a plausible future climate that has been constructed for the explicit use of investigating the potential consequences of anthropogenic climate change, which represent future conditions that account for both human-induced climate change and natural climate variability. An important application of climate scenarios take the form of what-if analyses. For example, what happens to our future climate if the greenhouse gas concentration doubles by the mid-21st century? Or, what might happen if the mean sea level rises by 1 meter and there is a storm surge of 1 meter on top of that? Since its inception in 1988, the IPCC has produced a series of comprehensive assessment reports on the state of our climate, its potential impacts, and options for response strategies. These IPCC publications have become standard works for reference, widely used by policymakers, scientists, and other experts. When the IPCC was beginning to write assessment reports, they commissioned climate scenarios. They convened scientists and modelers, provided them with terms of reference, and set the task of developing scenarios for future emissions. They then approved the scenarios developed for use in modeling studies and used the results in reports. The first climate change scenario, called IS-92, was released in 1992. It consisted of 6 global and regional greenhouse gas emission scenarios projected from 1990 through 2100. Much has changed since then in our understanding of possible future greenhouse gas emissions. In the year 2000, the IPCC released a second generation of projections collectively referred to as the Special Report on Emission Scenarios. These provided common reference points for a great deal of climate science research in the last decade. In 2007, the IPCC responded to calls for improvements to the SRES and produced a new set of climate scenarios called the Representative Concentration Pathways, or the RCPs. The RCPs are the latest iteration of the scenario process and are presented in the IPCC's Assessment Report 5, in preference to the SRES. The SRES scenarios use socioeconomic modeling to inform potential emissions trajectories, while the RCP scenarios are specifically named for radiative energy in watts per square meter added to the Earth's climate system by the end of the 21st century. For example, the RCP 2.6 scenario means that the climate system gains a total of 2.6 watts per square meter by 2100, while the RCP 8.5 means a gain of 8.5 watts per square meter. To put these values in perspective, the average energy input by the sun into our atmosphere is 78 watts per square meter. We can also think of these RCPs in terms of greenhouse gas emissions. For example, the RCP 2.6 scenario represents greenhouse gas emissions peaking in about 2020 and declining thereafter, representing a situation that reflects more sustainable growth and development. The RCP 8.5 scenario represents continuously increasing greenhouse gas emissions throughout the 21st century, representing more fossil fuel use and less sustainable development. Comparing and contrasting the different RCPs allows us to evaluate the consequences of implementing various climate, social, and economic policies that affect greenhouse gas emissions. Quite recently, in 2021, the IPCC released a draft copy of the 6th Assessment Report with the new emission scenario known as the Shared Socioeconomic Pathways, or the SSPs. These SSPs are now being used as important inputs for the latest climate models to explore how societal choices will affect greenhouse gas emissions and therefore how the climate goals of the Paris Agreement could be met. The new SSPs outline 5 pathways that the world could take. They include a world of sustainability-focused growth and equality, or SSP1. A middle-of-the-road world where trends broadly follow their historical patterns, or SSP2. A fragmented world of resurgent nationalism, or SSP3. A world of ever-increasing inequality, or SSP4. And finally, a world of rapid and unconstrained growth in economic output and energy use, or SSP5. The SSPs show that it would be much easier to mitigate and adapt to climate change in some versions of the future than in others. They suggest, for example, that a future with resurgent nationalism and a fragmentation of the international order could make the well below 2 degrees Celsius Paris target impossible. Unfortunately, without time travel into the future, we cannot know exactly how well any particular RCP or SSP represents how the world will develop economically and socially in the decades ahead. The choices we make will contribute to a range of plausible climate futures, and the IPCC scenarios are intended to cover that range, offering a systematic approach to model socioeconomic pathways for the rest of the century and beyond. The scenario that becomes a reality will depend on the choices we make, both now and in the future. The climate scenarios, which we have discussed earlier, are used to calculate the probable future climate. The resulting climate projection models are produced through a method called downscaling. First, let's understand the climate models. Our climate conditions are the result of complex interactions among processes occurring in the atmosphere and the ocean. These processes operate at global and local scales and are influenced by other factors including the land surface, polar ice sheets, and the sun. This is why we experience different climatic conditions in different places. We use models in our daily lives. For example, we use architectural models to show how certain buildings might look if we were to build them. We use models in engineering to test designs before investing in them. And climate modeling is conceptually similar. A climate model is a simulation of all the factors that can affect the Earth's climate. Some of these factors are things that don't change, such as distance from the sea, elevation, and latitude. Some of the factors are things that do change, such as the seasons, volcanic eruptions, and air pollution. We use climate models to look at our future and see how it would unfold, depending on what choices we make. For example, as we move towards the middle and then the end of the century, what will our average annual temperature look like? The answer depends on whether we follow something closer to a lower emission scenario or something closer to a higher emission scenario. The main group of climate models that would depend on are called the global climate models, or the GCMs. GCMs are computer simulations that attempt to capture and simulate all of these processes based on our current knowledge. The basic building blocks for GCMs are grid cells, which divide the Earth's surface into areas typically measuring between 250 and 600 kilometers, which represents the resolution of the grid. Each grid cell contains climate-related physical information about a particular location, such as its key physical, chemical, geological, and biological climate processes, which are represented by mathematical equations. Determining how many grid boxes we want in the model requires a tricky balance between accurately representing the important physical processes of the Earth's climate system and factoring in the real-world constraints involving computational power needed to solve equations in more grid boxes. Many institutions develop and use climate models. The World Climate Research Program, or the WCRP, hosted by the World Meteorological Organization, coordinates research activities on climate modeling worldwide. The Coupled Model Intercomparison Project, or the CMIP, under the WCRP, is a global framework for analyzing the output of GCMs. Simulations from Phase 5 of this project, or the CMIP-5, were used by the Intergovernmental Panel on Climate Change in the development of their 5th assessment report. There is simulation data from around 48 GCMs available in the CMIP-5 archive. GCMs provide us with projections of how the climate of the Earth may change in the future. These results are the main motivation for the international community to make decisions on climate change mitigation. However, the impacts of a changing climate and the adaptation strategies required to deal with them will tend to occur on more regional and national scales. We therefore need much greater detail and a more accurate representation of localized climate information. In other words, as noted earlier, GCM grid boxes typically have a resolution of between 250 and 600 kilometers, which is a coarse resolution. Too large if we want to know what climate change has in store for a specific country, state, or even a city. This is where downscaling is required. Scientists take model outputs calculated on a larger scale and reduce or downsize that output to a smaller scale. So downscaling is a method that allows climate data or information to be generated at a finer resolution than the kind generally obtained from GCMs. In other words, it is a process of generating higher resolution data or climate change information from relatively coarse resolution GCMs, giving it greater relevance for adaptation and policy decision making. Downscaling uses the assumption that the local climate is driven by large-scale climate characteristics, but modified by some local factors such as mountains and proximity to oceans and lakes. The Regional Climate Model, or the RCM, is the downscaled version of the GCM and has a much higher grid resolution than GCMs. However, the quality of the information coming from the RCM depends on the quality of the information provided by the GCM. So ultimately, it is important to know the strengths and the weaknesses of the GCM. There are two established methods for downscaling the GCMs: the dynamical and the statistical or empirical method. These techniques are complementary and both have strengths and weaknesses. Firstly, let us understand the statistical downscaling method. Statistical downscaling compares GCM output for a particular period in the past with observations during that same time. By comparing model projections and actual climate data observations, a statistical relationship is established between global and regional climate patterns. This statistical relationship is then applied to predict future climate projections. However, this approach is based on the assumption that the statistical relationship established will continue to hold in the future. While there are different ways of building statistical relationships, the simplest one is the transfer method, which includes a technique called the delta method. The delta method determines the projected change, or delta, of a climate variable from the GCM and applies it to the observations. For example, if we are interested in the average temperature in Bangkok in the future, we can look at the projected change of temperature from a GCM and apply that change to the observations in Bangkok for the same time period to examine what temperatures may look like under a changing climate. Other methods include weather typing, also known as pattern classification or analogs, and weather generators, which use more advanced statistical relationships. As with any downscaling technique, there are also disadvantages. Firstly, statistical downscaling requires a long observational record to build a robust statistical relationship. At a minimum, this usually requires about 20 years of data, and the more observation data, the better. In many cases, The observation data for temperature and precipitation are available, but observation data for parameters such as evapotranspiration, solar radiation, and humidity are usually hard to find. This is a weakness if we are interested in changes to things like soil moisture, since most statistical downscaling techniques focus on variables with a long observation record. Secondly, statistical downscaling assumes that the statistical relationships developed based on observation in the past and GCM output for the same period will continue to hold in the future. However, given that climate change may alter the way that climate functions, this statistical relationship may not remain consistent in the future. Finally, the results from the statistical downscaling can be affected by errors in the GCM, since it does depend on the GCM information being reliable to establish the statistical relationships. If the GCM has errors in a particular region of interest, those errors can spread to the results of the statistical downscaling. Dynamical downscaling is a method where GCM output is simulated to smaller scales using another higher resolution dynamical model called a regional climate model, or RCM. The regional model for the area of interest is chosen such that it is large enough to capture important weather processes in the region of interest, while ensuring that this region of interest is far enough from the boundaries of the model. For example, if you're interested in the future climate of Bangkok, you might choose a regional model domain which also encompasses other provinces connected with Bangkok. The RCM output is further analyzed for information about climate change within the region of interest. This process of dynamical downscaling is a one-way street from the GCM to the RCM. That is, the results of the GCM directly affect the regional model output, but the regional model does not impact the global model. There are different approaches to dynamical downscaling: direct dynamical downscaling, which is explained above, and the pseudo-global warming approach, or PGW. The PGW approach uses current climate reanalysis, or global climate data observation, and climate change signals, which are monthly average differences between current and future climate projections produced by a GCM to produce a pseudo-future climate projection with a much higher resolution. Our S8 downscaling uses this PGW approach. As with the statistical downscaling method, dynamical downscaling also has some disadvantages. Firstly, the method is computationally expensive as it requires a large amount of computing power and resources. Secondly, the results from the dynamical downscaling can be affected by the errors of the GCM, since it does depend on the GCM information being reliable to downscale the required information. If the GCM has errors in a particular region of interest, those errors can affect the downscaling accuracy. Finally, RCMs and GCMs may suffer from what we call boundary issues, problems at the interface between the GCM and the RCM. This issue arises because of the one-way interaction between the GCM and the RCM, leading to mismatches or unrealistic values of atmospheric variables like moisture or temperature at the RCM boundaries. So, which method should be used? There is no single method that is considered the best one by the scientific community, as each downscaling method has its own strengths and weaknesses in its application. The best option to use depends on the application and availability of resources. In summary, in terms of future climate projections, downscaling is a procedure used to produce higher resolution data from coarse resolution GCMs. The ability to downscale the current climate does not guarantee the accuracy of downscaling in the future, as we know that no predictions of the future can be made with 100% certainty. There are three main sources of uncertainty in climate downscaling. They are natural variability, downscaling methods, and human behavior. Natural variability is the result of interactions between components of the climate system, such as the atmosphere, the ocean, and the biosphere. These natural variations in the climate system cause temperature, precipitation, and other aspects of climate to vary from year to year and even decade to decade, making them an important source of uncertainty. There are also extreme events, a mostly local phenomenon, occurring at smaller scales than the GCM model. They are difficult to model because they deviate from the average. Downscaling uncertainty results from the many factors that interact to determine how the climate of one specific location will respond to global scale change over the coming century. As scientists do not have a limitless supply of computing power at their disposal, Models must divide up the Earth into grid cells to make the calculations more manageable, which means that at every step of the model through time, it is necessary to calculate the average climate of each grid cell. However, there are many processes in the climate system and on the Earth's surface that occur on scales within a single cell. For example, the height of the land surface will be averaged across a whole grid cell in the model, meaning it potentially overlooks the detail of physical features such as mountains and valleys. Similarly, clouds can form and disperse at scales that are much smaller than the grid cell. Scientists use parameterization to solve problems with such variables using computer code rather than being calculated by the model itself. And this is one of the main sources of uncertainty in climate models. Human activities continue to increase the amount of greenhouse gases in the atmosphere, which in turn affects the climate. To predict the future climate, we need to have an idea of what the future levels of atmospheric greenhouse gases are likely to be. For example, if we continue a carbon-intensive economic growth path, burning high quantities of fossil fuels, there will be higher concentrations of greenhouse gases in the atmosphere. In that case, the effect on climate is likely to be greater than if we decide to reduce our emissions. Climate models typically use these different scenarios to give a range of potential future climate conditions to provide plausible future scenarios. Therefore, uncertainty in human activities will lead to uncertain future projections. Despite uncertainties in climate projection, climate scenarios are important for picturing the future climate and understanding its impacts. These uncertainties should not prevent the understanding of responses to plausible climate change scenarios. We cannot wait for perfect models and methods, and need to make choices today based on the best current scientific information to engage in responsible planning for a plausible range of climate futures.